For the purpose of making electrical and electronic circuits, it is important to be able to control the flow of the current and the size of the current. And for this purpose, there are many commercially made resistors. These are components, looks a bit like this in one of the more common forms, a little tube with some color on it. The purpose of this component is to provide specific values of resistance for the circuit, so as to adjust the currents to the value that we want. Just as an example, one of the commonly available, meaning that you can buy quite easily in electronic shops, one of the type of resistors, as they're called, that are commonly available have carbon films inside. So these are thin. Well, carbon is a conductor of electricity. So these resistors have thin films of carbon inside, adjusted to different perhaps shapes and size to provide some specific values of resistance. And it is possible to buy these resistors. I think they're usually quite small and cheap, for values of resistance, at least for those that are made from carbon films. They can be made to resistance values ranging from maybe 1 ohm to 10 mega ohm. If you remember, mega means million, so from 1 ohm to 10 million ohms. So you can buy little pieces of this with this resistance within this range, and you would often see little lines of color on this resistor, and the colors here mean something. Each color represents a number, and it's supposed to tell us the value of the resistance. So just I shan't go into the details, but just as an example, the blue color there represents the number 6. The green color represents the number, might as well use color for that. So the blue color represents the number 6. The green color there represents the number 5. And the red color actually represents the number 2. But the way it is arranged is that the last, or rather the third band of color, and it varies with the resistor, so it takes some getting used to. So the red line in the third position, red means 2, but the red would probably mean 20. So in this case, it means that this color code would most likely represent a resistor with a resistance of 6500 ohms, for example. Now for that's as much as I'll say about the resistor. What I'd like to talk about next in this video is I would like to talk about the resistance inside the battery as well. Now, ideally, we would like a battery. For example, if you buy a battery and it says 1.5 volts on the battery, ideally we would like the battery to give 1.5 volts when we connect it to a torchlight or our DVD player or any other electronic things that we have. Okay, because after all, that's what it says and we pay for it. But unfortunately, in in reality, the battery itself has resistance. Battery itself has resistance. And what that means is that when a current flows, that resistance would actually take up some the voltage. Now let's see how this works. Let me for this example, I'm just going to use some example value of resistances. Now for the common battery that we would probably buy in the shop, the resistance within the battery is probably about a few ohms. So I'm just going to say that it is about, for this example, about 3 ohms. So let's say the battery itself gives a resistance of 3 ohms to the current that flows through it when the battery is connected in a circuit. And just for this example, I'm not going to use the 6500 ohm resistor. I'm just going to take as an example, say a 6 ohm resistor, just a 6 ohm. So for now, just ignore the color coding. So let's say this is a 6 ohm resistor. And then the battery offers an internal resistance of 3 ohms. Well, then what happens when the current flows through it? Well, when the current flows through it, the current has to do work as it goes through the resistor, because it's like pushing an object over a table that has friction. Okay, so the current has to do work as it goes through. And what this means is that the 1.5 volt of the battery, if you remember what 1.5 volt means, 1.5 volts means that 1.5 joules of work, right, is done on every 1 coulomb of charge. Okay, so if the 1.5 volt is the potential difference between the resistor, then when 1 coulomb of charge goes through the resistor, then 1.5 joules of work is done. But in this case, the 1.5 volt is not just a voltage across the resistor. The 1.5 volt here represents, in a sense, the work done around the whole circuit, including the 3 ohm resistor. So the 1.5 volt here means that 1.5 joules of work is done on 1 coulomb when the 1 coulomb moves around the whole circuit, right? This is for around the whole circuit, and not just for any part of it, not just for this particular resistor alone. So that has to include that. So the 1.5 volt, meaning that if 1 coulomb of charge is pushed around the circuit once, that 1.5 volts has to be that 1.5 joule of work that is done has to be split between this resistor, this 6 ohm resistor outside the battery, and the 3 ohm resistance inside the battery. So part of the 1.5 joules go here, part of the 1.5 joules go there. Right, but exactly how much? Now let me do a quick estimation or calculation of how much. Now the way to do it is to think about Ohm's law. V is equal to IR. Now if you look through this, you see that the resistance is different there and there, but the I has to be the same. The current I, has to be the same as it goes round and round. because it's just one single loop, and the same charge just goes through the whole circuit. Okay, so it's the same current going through both the inside of the battery and the resistor outside, but the resistance is different. Okay, so if you think of I as a constant, in the sense that it's the same in the battery and outside the battery, if I is a constant, then the voltage and R are proportional, meaning that the voltage across this 3 ohm in the battery and the voltage across that 6 ohm over the resistor, it must be proportional. Okay. So this means that the voltage on the 6 ohm resistor, since this resistor outside is twice of the resistor inside, that's 6, this is 3, it means that the voltage across the resistor must also be twice of the voltage that is used for the 3 ohm. Okay, remember that the 1.5 volt is for the whole circuit, right? But for the 3 ohm resistor itself, it needs to take up some voltage as well. So this means that this voltage would be divided between the two resistances in the same ratio as the resistors. So let me write this down. If I say that there's a voltage of V1 associated with this 3 ohm resistor, and a voltage of V2 associated with this 6 ohm resistor. Okay. Now this means that if I substitute it into these numbers here, I would get for V1 would be equal to I times the 3 here. So I times 3. And the V2 there would be the same current I times the resistance of 6. So V2 is equal to I times 6. Now if I divide the two, I get the ratio. The ratio is that V2 is to V1 is equal to, that's 2 there, V2 is to V1 is equal to 6 is to 3, which is 2 is to 1. So this means that all I need is to look at the resistances and think, right, the ratio of this resistance to this resistance is 2 is to 1. So this overall voltage, if you like, must be split in the same ratio between the two. So also 2 is to 1. Now what happens when 1.5 volts is split in the ratio of 2 is to 1? Like this, 2 is to 1. The 2 is to 1, you can think of it as 3 parts, and 2 is the 2 parts and 1 is the 1 part. So 2 parts of this goes to there and 1 part of this goes to there. So since this is 1.5 volts, it just means that 1 volt goes here and 0.5 volts go there. Alright, because if you take 1.5 volt and you split it up into 1 volt and 0.5 volt, then this ratio is 2 is to 5. Alright, that's the ratio. So therefore this is the V2 over the resistor outside, and that's the V1 over the resistance inside. So, and what this means is that 1 volt over here means that if 1 coulomb goes around the circuit once, right, as we know 1.5 joules of work in total is done, but of this 1.5 joules of work, from what we understand here, 1 joule of work would be done on the resistor and 0.5 joules done on the resistance inside the battery. So the work is split into these two parts. Now let me summarize these ideas that I have talked about. First, by defining some terms. Now, okay, that's the resistance outside the battery, which we are kind of more familiar with by now. Now, this resistance that's inside the battery, it's a little bit abstract, because we don't normally see a battery as a resistor. So we describe this value, this resistance in the battery. We describe it using the term internal resistance. So internal resistance is simply the resistance in the cell. This is in the cell. So that's one. Now the other thing is the 1.5 volts. The 1.5 volt. This is I've talked about this mostly up to now as the voltage given by the battery. Now, but in this case, as we have seen, the 1.5 volt is not really the voltage across the resistor itself. The 1.5 volts supplies the work done for both the resistor outside of the battery as well as the resistor inside the battery. So if I continue to use the term voltage for the 1.5 volt of the battery, that's going to be confusing. That's going to be confusing because clearly when I connect the battery to this 6 ohm resistor, I don't get 1.5 volt. All I got was the 1 volt. See, so so I've not got my money's worth. I mean, I bought this battery to get 1.5 volts for whatever I want to use, but because of the internal resistance, which they never tell you about. I mean, if you buy a battery, no battery is going to say on the box that it has a 3 ohm resistance that's going to take away some of your 1.5 volts. Okay, so that means that I have not got my money's worth, and more importantly, I don't actually get the full 1.5 volts when I connect this battery to my electronic device. In this example, let's say I only get 1 volt. Okay, so internal resistance has this effect of decreasing the voltage that actually goes to the, we can call this a load, right? Something that the battery does work on. So it's better to reserve the term voltage for the voltage, for the number of volts that actually get to the device or the load. So I might as well write this term down. So the load, I think of the term load is sort of an abstract term, but for example, it might be a light bulb. It might be say my DVD or my radio, for example. Okay, that's my load. And if I reserve the term voltage for just this part, just the part outside the battery, then what do I call this voltage from inside the battery? What do I call this overall 1.5 volts supplied by the battery? Okay, we need another name for it. Now we call this the EMF. Now EMF stands for electromotive force. Okay, and to be very, very precise, the electromotive force is the work done on a unit charge, right, around the whole circuit. So EMF is the work done on a unit charge, or to bring the unit charge around the whole circuit. So that's EMF. So we now have a more specific name that refers to the 1.5 volts of the battery. So next time you buy a battery, the 1.5 volt is not the voltage you're actually going to get, or may not be the voltage you're actually going to get when you connect this to your torchlight or your radio. Right? The 1.5 volt is the EMF. Whatever you get when you connect this to your torchlight, let's say, is the voltage that you get after some of that EMF is used up to overcome the battery's own internal resistance.